Hey Chem fam, we want to do a couple calorimetry practice problems, and I'm taking some off of our calorimetry worksheet, and this is number 6 currently, but it says that we have a 50-gram piece of iron. So what I'm going to do, since calorimetry we mix two things together and look at the heat exchange, I'm going to write down everything I know about both of them. So first of all, for my mass here, I have 50 grams of a piece of iron, and that's given to me right here. I also know that it's at 100 degrees Celsius. So that's its starting temperature. It's 100 degrees Celsius. All right. I then put it in 110 grams of water. So my water sample is the second sample, and I know I have 110 grams of that. And whoops, that should end up being mass, not grams. Let me fix that up. There we go. Now that's the mass of water is 110 grams. And I have 23 degrees Celsius initial temperature for that water of H2O. All right. I want to know what the final temperature would be. Now we know when we put the hot iron into the cold water, which, by the way, wow, I'm on a roll here, aren't I? 23 degrees Celsius is the temperature. We put the hot iron into the cool water. We know that the iron will cool down and the water will heat up. Now, since we're doing stuff with heat transfer in that, we should make note of the specific heats of both objects. Iron specific heat is about 0.45 joules per gram degree Celsius, and liquid water is about 4.184 joules per gram degree Celsius. Now that we have all that information, don't forget that iron will lose the heat and water will gain all that heat, which means that the amount of heat iron loses, water will gain. And because of that, we know that we can set those specific heat equations equal to each other, mc delta T. Now, instead of worrying about that loss and distributing that negative and maybe getting confusing, remember when we do our equations, we just want to make sure that both of the change in temperatures end up being positive. If they do that, then this equality will be just fine. All right, so that's just a shortcut. Again, you could do everything normal with the change in temperature is always final minus initial. You just have to distribute the negative. But otherwise, if you just keep the change in temperatures positive, it ends up being the same thing as well. So it's just a little shortcut. Okay, so let's start doing that. We're going to use these equations, mc delta T, and start plugging in. So on the left side, I'm going to take my iron. So my mass is 50, M. My C is the specific heat, is 0.45. And my change in temperature, I have to think about. Now, iron, remember, is hot and will end up having a final temperature that is lower. It'll be cold. In order to subtract either initial minus final or final minus initial, we want it to end up being positive. So that's why we would take the initial temperature, 100, and subtract it from the final temperature that we know is less. When you take a bigger number minus a smaller number, we know that'll always end up being positive. And as I said, we want to make sure that the change in temperatures for both of these end up being positive, even though we know that typically it's final minus initial. Whenever you take the hotter item in calorimetry, just do initial minus final so that the change in temp equals positive numbers and you'll be just fine. All right, that's just one little tweak. Otherwise, everything else stays the same like we've been doing. Now, on the water side, you have 110 grams, that's your mass, and you have a specific heat, the C value, which is 4.184. Now, remember, we got these values. It's not in the problem. We looked them up on our chart. So this value and this value is just something we look up on a specific heat chart. So that's nothing that was given. All right. Now that we know that we have cold water at 23 degrees, and we know when you put that hot lead in, the final temperature of the water will go up. That means the final temperature will be bigger, so we want to take that and subtract the initial temperature. Why? Since the final temperature will be bigger, we know a bigger number minus a smaller number will give us a positive value. And again, the change in temperatures, we want both to be positive because it's a shortcut to end up giving us that equality where we have losing heat for iron and gaining heat for water. Okay, now we can just rock that out by starting to do our math. So I'm going to take 50 times 0.45 and I'm going to then distribute that over into my parentheses. So let's start rocking all that out. Multiplying 50 times 0.445 gives you 22.5, and that is going to still be multiplied into that equation. And then I'm going to do 110 times 4.184 on this side, and that gives me 460.24, and that's going to be final minus 23. Now I'm going to distribute that number to both of them. So 22.5 times 100 ends up being 2,250 minus 22.5 times TF, since you're distributing. And then to do 460 over to TF, it is just the same number times TF minus 460.24 times the 23, and you end up getting about 10,585.52. All right, now we need to combine like terms. We can do that. Let's turn my subtraction into adding a negative. I like to do that. You don't have to, but that tells me that I need to add 22.5 TF to both sides, 22.5 TF to both sides. That will cancel out. And also, I'm going to get rid of this guy here to the other side. So I'm going to add a positive 10,585.52 to both sides, 10,585.2, right? That will cancel out. What do I end up with now when I add these guys up and these guys up? Let's do that. I end up with about 482.74 for the final temperature, times the final temperature, that is. And when I add up the 10,000 plus the 2,000, I end up with about 12,835.52. All right, getting super close. All we have to do now is get TF by itself. So I need to divide both sides by 482.74, divide by 482.74. Sorry, I'm running out of room there. That will cancel that out and that out. So I'm left with TF on the right side. And when I take this, 12,835.52 divided by 482.74, I end up getting about 26.6 degrees Celsius for my final answer. Now, let's make sure if that temperature actually makes sense. You had hot iron at 100 degrees. Okay, let me change my color here. So hot iron was 100 degrees. Water started at 23. You put the hot iron into the water, and now the temperature of the water rose to 26 degrees. Yeah, that makes sense, because you had 110 grams of water and you put 50 grams of hot iron into it. That should make the water heat up just a little bit, and it did. Remember, water has a high specific heat capacity, so it is hard for water to heat up. So that's not a shock that the temperature didn't change dramatically, that it only went up about 3.6 degrees. So overall, this seemed to make sense and work out and be a realistic answer. All right, there's one equation for you, ChemFam. All right, let's also look at number 9 so that we can get another problem of calorimetry in. I have a 70-gram piece of metal, so I don't know what this metal is, but I have 70 grams of it. Okay, that's my mass. And I know it's at 100 degrees, so its initial temperature is 100 degrees Celsius. Sorry for my sloppy writing there. Let me shift things over so I can write better. Okay, that looks good. Now, it's in 150 grams of water. So I've got H2O, and I've got a mass of 150 grams. Now, reading this, it looks like the water's initial temperature is at 23 degrees Celsius. And after these two objects mix together, their final temperature is 30 degrees Celsius. So we know the final temperature. The question we are looking for is what is the specific heat of this metal, and what metal could that be? So we are going to look for the C value for the metal. We know for liquid water that C is 4.184 always. So I think we have enough information in order to solve for the specific heat. Now remember, the metal is going to lose heat, and whatever heat it loses, water is going to gain, which is why we can set our two equations of MC delta T equal to each other. Now remember, we always want both of our changes in temperatures to be positive. By doing that, that's a shortcut to take into account that loss of heat versus gain of heat. And by doing that, our math just comes out a lot easier and we don't have to worry about negatives. So let's do that and start plugging into these two equations so that we can solve for this specific metal's specific heat. All right, let's do it. The metal is 70 grams. We don't know its specific heat, and we need to take the change in temperature so that it'll be a positive value. Well, that means we're going to take the 100 degrees minus its final temperature of 30 degrees. That way, it'll be a positive number. Now, for the water side, we have 150 grams, and we know that the specific heat is 4.184, and the change in temperature we have to keep positive, so 30 degrees is higher than 23 for water, so we're going to start with the final and minus the initial 23 degrees. And that's a 3 there. Sorry about that at the end. All right, let's do our math to figure everything out. 100 minus 30 is 70. Okay, and 30 minus 23 is 7 times 4.184 times 150. All right, let's rock out our math so that we get eventually C by itself. So 70 times 70 here is going to give us 4,900. That's a 4. And 150 times 4.184 times the 7 gives us 4,393.2. To get C by itself, just divide both sides by 4,900. And you end up getting C all alone, which ends up being about 0.897 joules per gram degree Celsius. Now that is the specific heat of the metal, but what metal is that? Well, let's look on our chart to figure out what's closest to that number. Looking on the page in the specific heat chart, it looks like the closest metal to 0.89 specific heat would be aluminum. So there you go. We not only found out the specific heat, but it helped identify what metal we're actually dealing with, and calorimetry helped with that. All right, ChemFam, hopefully that helped out a little bit more in setting up some of the problems and getting a little bit understanding that's better for specific heat and also, of course, calorimetry. Take care.